In this video, we're going to study linear differential equations. And in particular, we're going to study first-order linear differential equations and the method of integrating factors, which is a wonderful way to always find a solution to a first-order linear differential equation. There is one heuristic that weaves its way throughout a lot of mathematics, which is that linear equations tend to be easier to understand and manage and to manipulate and develop theorems about than nonlinear equations. And in differential equations, this is going to be true as well, that studying linear differential equations is going to be, relatively at least, easier than studying nonlinear equations in general. So what is a linear differential equation? Well, this is an example of it. And it looks quite messy here. I mean, there's lots of squared terms, there's a sine of x term, there's an exponential term. But notice the following very important fact. The function y prime, and the function y double prime, all of those are what we're going to call linear. It's not like it's y prime squared or e to the y. The y prime just sits by itself to the power of 1 and is multiplied by a coefficient function. So the coefficient function of y double prime was x squared. The coefficient function of y prime was sine of x. The coefficient function of y was 3, and if you like to think of it this way, the coefficient function of just 1 was e to the x. So this is an example of a linear, second order, because there's two derivatives, differential equation. More generally, a ODE, an ordinary differential equation, is called linear if it obeys the following property. It's just a bunch of derivatives, y prime, all the way up to the nth derivative. Little bracket with an n inside of it denotes the nth derivative of y. And then each of those has a coefficient function, which I call the a0 of x all the way up to an of x. And then that's it. They're just added together. On the right-hand side, this might then be equal to a final function, which we'll call b of x. So that's the definition of a linear ordinary differential equation. One more buzzword for you is if that b of x, if that right-hand side, the thing that's multiplied by just the function 1, no y's at all, if that is 0, we additionally call it a homogeneous linear ordinary differential equation. Now, if you've taken linear algebra, and it's okay if you haven't, then you've seen these types of terms before. For example, if you had a linear equation, it might represent, for example, a line or a plane. And if that linear equation was additionally a homogeneous linear equation, so there was no constant term, it'd be a line or a plane through the origin. And we had this whole theory of linear algebra, which was really well developed because we love linear equations as opposed to nonlinear equations, which we still love, but are a little bit more challenging. And while there's no derivatives in linear algebra, a lot of that metaphor is going to be true here as well. Now, in this video, we're really going to focus on first-order linear differential equations and have a method called the integrating factor method to be able to solve them. So the first thing I'm going to do is write down a generic first-order linear ordinary differential equation. It's a mouthful, and what we're going to call its standard form. So the standard form uses a little bit of a different notation than what I just introduced with the an and the an minus 1 and so forth. In the standard form for a first order, it goes y prime, which is basically saying a coefficient function of 1. Then y gets multiplied by p of x, so the coefficient function of y. And then on the right-hand side, you have this f of x. If you ever had it written in the previous form where there was also a coefficient function in front of the y prime, you would just divide it out to get your p of x and your f of x. Okay, so that's the form, but how can I solve this? Now, I want you to imagine something. Imagine it was the case that p of x was equal to 0. If p of x was equal to 0, then I think you could solve this differential equation. You just have y prime on the left, you'd have f of x on the right, and you could just integrate. A derivative is a function, you could just integrate and get the answer. That is, if ever your differential equation is just written as a derivative by itself is just equal to the function of the independent variable, then it's easy, you just integrate. But we don't have the fact that p of x is equal to 0, and we're sort of going to try and fake it by a method called the method of integrating factors. So here's how it works. I'm going to take the same differential equation, but I'm going to multiply it by some function I don't yet know what it is, called r of x. R of x is our integrating factor. I'm allowed to do this. I mean, I can do the same thing to both sides of an equation. I could multiply both sides of an equation by some non-zero function, r of x. Now, what I would like to do, and I can't yet do it, but what I want to be able to do is take that left-hand side and just rewrite it as the derivative of something, perhaps the derivative of the integrating factor r of x multiplied by y. And the reason that I would like to be able to do that is if I had, then on the left-hand side I'd have a derivative, on the right-hand side I'd have a function of x, and I could just integrate both sides with respect to x. That'd tell me my r times y divided by r, and that would tell me my y. So I would love if I could write that left-hand side in this format as the derivative of r of x times y of x. But I mean, it doesn't at all look like that right now. Well, what if I tailored the r of x to be exactly the thing I needed, such that it was possible to rewrite the left-hand side in this way? So how could I find that? Well, if I could write it in this way as the derivative of r of x times y, that's the derivative of a product, and we would have the product rule. So let me expand out the product rule. It would say r of x times y prime plus r prime of x times y. That would be what we'd get. Now, if I compare what I want to what we have, well, there's a first term that's identical for both of them, the r times the y prime. That's the same. Okay, looking pretty good. But the second term is quite different. In what I have, it's r times p times y. What I want it to be, it's r prime times y. At least there's a y in both, so I could actually just get rid of the y in my comparison. It's saying r times p would have to be equal to r prime. So again, I'm just trying to find a function of r of x that would work out to make it nice the way I want it to be. And if that was to be the case, then these two things would have to be equal. Okay, so let's just play around with that. Let's just set those two things being equal and just see what we get. This here is a differential equation. It's actually a first order differential equation in the variables r and x. Okay. In fact, I can do more than that. It's not only just a first order, it's a separable first order. So let me just go and separate it using the method of separation of variables. I'm going to divide out by the r of x on both sides, and then I'm going to integrate with respect to x on both sides. So I get r prime over r on the left, and then the integral of p of x on the right. So now I'm solving some integral. Well, the left-hand side I can do, it's going to be a logarithm. If my r of x is positive, I'll say more about that in a second, then it would be the logarithm of r of x is equal to the integral of p of x. Now, I don't have a p because I'm doing a general example right now, so I can't evaluate the right-hand side. I'll just leave the right-hand side as the integral of p of x dx. If you had a specific p of x, you could go and do this. But regardless, I have a logarithm. I want to get rid of that logarithm. I'm going to take an exponential. And so my r of x is e to the integral of p of x dx. So this is an answer. This tells me what the integrating factor is that I should choose. It's that function. Take your p of x, integrate it, it's e to whatever you get. Two little notes here. First of all, I could have chosen this to be negative as well. It wouldn't matter though. I mean, I was multiplying every single term of my differential equation. If I multiplied it by a negative or positive, doesn't matter. I'll just assume it's positive. Second thing, when you do an integral, well, you get a constant of integration that should come out of that. But I don't care about the constant. Again, I'm trying to find some r of x that satisfies my property. Well, I'll just choose c equal to 0, so I don't have to think about the constant. As long as it works, it works. Nevertheless, here it is. I have my r of x. Okay, so let me go back just a moment to remind myself of what it was that I was talking about. This was the previous slide we compared a few minutes ago. And what we were saying was, we wanted to find an r of x such that we could have this nice thing that we understood. The derivative of r of x times y on the left-hand side was set to be just some functions of x on the right. R of x times f of x. So that's what I'm hoping to get. And indeed, I found an r of x such that this is going to be true. So now I actually want to solve this equation. Well, I can do that. It's just a derivative on the left. Indeed, that was the whole point. I can now just integrate this. So what do I get? Well, integrate both sides, and so you get an integral of r of x times f of x. On the left, it was r of x times y, so I need to divide out by the r of x. Final answer, y is 1 over the r of x, and then the integral of r of x times f of x, where that r of x is the thing we computed previously, e to the integral of the p of x dx. And that's my answer. By the way, one little thing I've noticed on tests that for whatever reason, students often forget the 1 over r of x factor. They do everything else correctly, so just make sure that's not going to be you. Either way, what we have is a solution to the original differential equation. Indeed, I encourage you to verify this by taking the derivative, plugging it in, and making sure that you get whatever you get. Now, I owe you a concrete example of this where I tell you the f of x and tell you the p of x and we go and compute it out. I will do that in the next video. But while we're still in the slightly more general and abstract sense, I want to focus a little bit on what the existence and uniqueness consequences are when you have this solution and use this methodology to solve a first order linear differential equation. Because the first thing I want to note is, when I look at this, there's two integrals here. The integral of p of x, and then the integral of r of x times f of x. So as long as you can do those integrals, you get a solution. That is, I have the following existence and uniqueness theorem. It says that if f of x and p of x are continuous, which is sufficient for me to be able to integrate them, and they're continuous on some interval a, b, well, wherever those are continuous, wherever I can do the integrals, I get a y. And it's not just existence, it's a unique solution. Because if I think about my methodology, it says, if there's a solution to that equation, right? We started by setting that equation equal to itself. Then the arguments that followed from there force the y to be of this particular format. Multiplying both sides of the equation doesn't change it, so you can multiply by your integrating factor. And then the fact that it was forced into this solution, that tells us this is the unique solution on that entire interval.